In our last video, we looked at drawing free body diagrams and what they look like when an object is stationary. I also introduced the concept that sometimes the object is starting to move. And what we're talking about is a net force acting on the object. So this video, we're going to clarify a few topics and understand how the dynamics of acceleration work. So just a refresher of where we were. I've got a table drawn here with a green object, and I've got the free body diagram with the arrows indicating the forces. I have a force of gravity here, it's 12 newtons, and I have a natural or normal force upward of 12 newtons. So they're equal in opposite directions. And if you look at the analysis, what does that mean? Well, what it means is that there's no net movement up or down. That's not quite right, but we'll come to that in a moment. Then what I have is I have a force of friction of 8 newtons, and I pull the object to the right with a force of 8 newtons. Once again, those forces are equal, so there's no net movement side to side. Once again, not quite right. That would be if the object was stationary, there's no movement. But what we're really looking at is we're using the free body diagram to determine if there's any net forces acting on the object. And what the net force is telling us is the object accelerating. And if all the net forces are equal, it is not accelerating. So now what we're going to look at is what if the accelerated force doesn't match the frictional force? So I've drawn 3 different free body diagrams, although they're almost identical. Please note that in all 3 diagrams, the gravitational and normal forces are all 12. They're all equal and cancel each other out. But in the first diagram, you'll notice that the force of friction is 15 and the applied force is 18, which gives me a net force of positive 3 newtons. And I'm using the positive here to indicate that the force applied is greater than the force of friction. Okay, and that's a common method of doing this, is that a positive indicates that FA is bigger. In the middle diagram, you'll notice that the net force is equal to 0 because the frictional force is 15 and the applied force is 15. In the third diagram, you'll notice that the frictional force is greater than the applied force, so we have a negative 3 newtons. Once again, the positive and negative indicate which one is larger, the applied force or the frictional force. Some people don't use a positive and negative, but simply use words or arrows to indicate direction in which it is larger. In this example, we could have used an arrow to the left and an arrow to the right to represent the positive and negative. Be very cautious because this could come back to be troubling later. So be very, very cautious on your use of signs. So now let's analyze these 3 different scenarios. And we'll start with the center one, because this is the one that's the most logical and that we've dealt with before. When the objects moving side to side cancel each other out, what we have is we have no net force. F net is 0. What does this mean? Well, it means that it's not going to change the object's state. Going back to Newton's first law, objects in motion will stay in motion, and objects at rest will stay at rest. So if this object was motionless, it will remain motionless. And if the object was moving, it will continue to move at the same speed that it was before. So now let's look at what happens when the applied force and the frictional force are not equal. So in the first scenario, what we have here is we have a greater applied force. And so we have a net force on the system of plus 3 newtons. So we have a positive net force. So once again, what does that mean? Well, that means that the force applied is greater than the force of friction. And so what that means, according to Newton's laws, is that if the object was motionless, it will start to move. And it's going to get faster and faster and faster as long as we still have that imbalance of the frictional force and the applied force. So if the frictional force remains at 15 and the applied force is at 18 and our net force is a positive 3, this object will get faster and faster and faster. And lastly, if the object was moving, it will continue to move. And like we said before, it will get faster and faster and faster. Once again, that is acceleration. The third scenario here is that the frictional force is greater than the applied force. What that means is that we have a net force that is negative. So the force of friction is greater than the applied force. Based on Newton's first law, if the object was motionless, it will remain motionless. Even though we have a net force that is a negative, the force of friction will not cause this object to start moving in a backwards direction. If the object was moving, it will slow down due to friction. It has a negative acceleration and it will continue to slow down until it stops. As long as the net force is negative. Once again, it will not start to move in a backwards direction. The friction will not cause it to move in a backwards direction. Remember, friction opposes the direction of the force that's acting on it, and it opposes the direction it's trying to move, but it will not move it itself in a backwards direction. Start. Let's begin by recalling our first dynamics equation according to Newton's law. The force is equal to the mass times the acceleration. F is ma. And that applies to any force. In this example, or in this scenario, it implies F net, but that could be the force of friction or the force of gravity, etc. So let's solve a nice easy question. So I've got a 2 kilogram object. I have a force of friction of 8 newtons and a force applied of 12 newtons. There's no reference here to the normal force or the gravitational force, so we're going to assume that they cancel each other out. What I'd like to know is, what is the acceleration? Well, first of all, I need to find my F net. And since I have my force of friction and my applied force, and we know that they're in opposite directions, we can solve that. Now, we have to be very, very cautious on how we do this in terms of our signs. I'm going to say that FA subtract FF gives us our F net. You'll notice that in this scenario, I have not written my force of friction as a negative number, even though it's in an opposite direction. Okay, so in this example, I'm going to have 12 newtons subtract 8 newtons, and I end up with a positive 4 newtons. Once again, that is telling me that this object is going to get faster. So now I know that my F net is equal to my mass times my acceleration. A little bit of algebra, I will see that my acceleration is equal to the F net divided by the mass. So in this example, we have an F net of 4 newtons. Now let's pause for a second. What's a newton again? This is 4 kilograms meters per second squared. Okay, so I'm going to tidy up my units here, and I want to focus on getting the correct units. That's 4 kilogram meters per second squared divided by the mass, which was 2 kilograms. I see that I have kilograms on the top and I have kilograms on the bottom. So my overall answer, if I watch my units, I'm going to see that my acceleration is equal to 4 divided by 2, which is 2 meters per second squared. And that is awesome because the acceleration units should be in meters per second squared. Remember, we need to indicate some kind of direction. Now, we weren't in the problem told that it was north, south, east, west, or to the left or to the right. So we will use a plus sign here to indicate that it is an exceeding or an increasing acceleration. Okay. If the problem had said that it was being pulled in a certain direction, then it would get faster in that direction. So I have another problem here, and it's always good to draw a free body diagram to represent our problems. And when we do this, we're always going to do it with the arrows or the vectors going from the center of the object. So the first one I'm going to draw is my force of gravity. It's always easy to figure out. So I have a 10 kilogram object being accelerated by the acceleration of gravity 9.81. So this is going to be a force of 98.1 newtons downward. Unless I'm told there's some other problem, we're going to make sure that I have my normal force opposite to gravity, 98.1 newtons. It doesn't move up or down. Thirdly, I have a force pulling it to the left. It has a force, now it's an applied force because we're pulling something, and it is smaller than 98. It's only 56, so I want to make sure I drew it proportionally smaller. And then I have a frictional force to the left. The frictional force is bigger than the applied force, smaller than the gravitational and normal forces. So I got to try and proportionally draw these things. So my force of friction is 79 newtons. So now I have a properly drawn free body diagram. So to solve this problem, first thing we need to do is find our net force. Once again, this is our force applied, subtract our force of friction. Be very, very careful about the use of positives and negatives. I'm treating this as a positive 56 newtons and a positive 79 newtons. So this would be 56 subtract 79. So what are we going to end up with? We see that we end up with negative 23 newtons of force. What does that tell us? This means that the object is slowing down. We could write this as a negative 23 newtons, but there's other ways we could do it as well. We'll come back to that. We want to find our acceleration. Once again, F net is mass times the acceleration. A little bit of algebra. A is F net divided by the mass. The acceleration will be negative 23 newtons divided by 10 kilograms. So we end up with an acceleration of negative 2.3. And looking at the units here, we're going to see that we are left with meters per second squared. Now, what does the negative mean? So this means it is slowing. So there's two ways you could write this. You could say that the acceleration is negative 2.3 meters per second squared, or you could say that the acceleration is 2.3 meters per second squared to the right. And I know it's to the right because my diagram told us that the object was being pulled to the left. And because it's being pulled to the left, the frictional force is greater. And that's where this negative has, we have to be careful. So we could say that the frictional force is to the left, so this object is slowing down, and the acceleration is in the left direction. Don't say it's negative to the right, because that is not correct. I suggest you pause the video and see if you can solve this scenario. Start by drawing your free body diagram, and then calculate all the forces that are involved. Once you have the forces, figure out the net force. And from your net force, you can determine the acceleration. Once you have the acceleration, you can finalize the velocity. Start by identifying everything that was given to us. So our mass was 5 kilograms. It was being pushed with a force, that's an applied force, of 15 newtons. It doesn't say what direction, so north, south, east, west, east, left, right. It had an initial velocity of 3 meters per second. It was pushed for a time of 4 seconds. We want to know the final velocity. And the last thing we were given is a coefficient of friction of 0.2. Once again, pause the video and see if you can finish it. Okay, here I go. First of all, I'm going to have a gravitational force, and I'm going to have a normal force, equal, opposite directions. I'll make my applied force to the right and my frictional force to the left. Now I need to figure out what those values are. My force of gravity is the mass of the object times the acceleration due to gravity. And so that is our mass of 5 kilograms times 9.81 meters per second squared. So that will give us an answer of 49.05 newtons. I'll write that as 49 newtons. That'll tell me that my normal force is also 49 newtons, opposite direction. To find my frictional force is Fn times mu. So what that's going to end up as 9.81. If I go to 2 digits, that'll be 10 newtons. My applied force was given to us. This is 15 newtons here. So now I have all of my forces. What I can do now is find my F net. My F net is my applied force, subtract my frictional force. So that would be 15, take away 10. So my F net is 5.0 newtons. So that's the overall net force, and it's positive. So what that's telling me that this thing is going to get faster. Okay, what's next? Well, I knew that my F net is mass times acceleration. So from there, I can calculate that my acceleration was my force divided by my mass. So in this case, my force, my F net, was 5 newtons. And my mass is 5 kilograms. Double check. There it is, 5 kilograms. That gives me an acceleration equal to 1 meters per second squared. That was convenient. Okay, we're not done. We know that our acceleration is the change in velocity divided by the change in time. Going back to our kinematics equations. So our change in velocity will be equal to the acceleration times the change in time. So that would be 1 meters per second squared multiplied by, was it 4 seconds? Time was 4 seconds. So my change in velocity is 4 meters per second. Well, I know that my initial velocity, let's take a look here. My change in velocity would be my final velocity, subtract my initial velocity. And we know the initial, so we could move that around, say that our change in velocity plus our initial velocity will equal our final velocity. So our final velocity will be I wrote them in the wrong order. Let's just keep them consistent here. My final velocity will be my change in velocity, which was 4 meters per second, plus my initial velocity, which was 3 meters per second, to give me a final answer of 7 meters per second. That is how fast the box is now moving.